about joint work with Greg Stevenson today. Some of you might be wondering about the picture on the right-hand side here. So in an earlier version of the preprint, there was a far more fanciful introduction, and my wife read it and it became a bit of an in-joke. But here's me hiding from a very large tensor triangulated category, waiting for him to pass so I can study the small things he's left behind to try and work out who he is. So my wife painted me this and I really like it, so I thought I'd feature it. So I just want to start with putting the hypothesis on the table, as always. So T throughout is going to be a rigidly, compactly generated T category. So for those of you who know these things, this should be quite familiar. For those of you who don't, I mean, I'm just enforcing some niceness conditions, which is going to make my life a lot easier. This means that we have a nice set of generating objects. And it also means that living inside here, I have this thing which I'll denote T omega of compact objects. So this is an essentially small triangulated category. So just so everyone has something in mind of what to think about, most examples we care about fall under this distinction. So, you know, the derived category of a ring, so our commutative ring here, that's one to keep in mind. If you're more topologically minded, you might care about SH. I want to decorate this with a G or something compactly, depending on who you are. Stable module category, it's always a fun one to have around. KG modules, you know, so all of the usual candidates appear under this hypothesis, so it's not actually that restrictive for what we want to do. And what's the overall goal? Well, with most things in maths, I mean, we want to understand these kind of big TT categories. And how do we do this? Well, we kind of want to probe their structure a bit, right? We want to look at maybe their certain subcategories or localizations of that TT category. And it's nice to have invariants which actually do this classification for us. So e.g., study the localizing subcategories. I mean, this in general is a very hard problem. I mean, we don't even know if there's a set of localizing subcategories, so we have to kind of adjust our expectations a little bit. So what's kind of the first approximation we have of this? Well, one thing that's been studied, you know, extensively throughout the years is you look at the set of thick tensor ideals in this essentially small thing, T omega. So thick here, for those who don't know, I just mean that it's a triangulated subcategory. We're closed under direct sums, and also we're tensor absorptive, just like in a ring. And we want to classify the thick tensor ideals of a triangulated category. This has been done by several people, but there's a really nice kind of universal invariant which tells us about these things. And this, of course, is the Balmer spectrum, which we'll come back to later. So this is a very nice topological space where certain nice subsets are exactly in bijection with the thick tensor ideals in T omega. So this is all very kind of well known, very useful invariant, very useful. This Balmer spectrum pops up all over the place, and computing it has led to a lot of kind of fruitful things. But we want to be a bit more adventurous now. So taking any thick tensor ideal, I can kind of inflate it up to the whole category T. So I can take the smallest kind of localizing thing that contains it. And these give a certain type of localizing ideals called smashing tensor ideals. So these are localizing subcategories, so triangulated subcategories closed under arbitrary coproducts. So S, including T, and we ask, so these are these subcategories where this inclusion I admits a coproduct preserving right adjoint. So given any thick tensor ideal, I can always inflate it up and I get one of these things. And you might ask, do I get all smashing tensor ideals doing this? And this is a good question to ask. So if this lock gives, this is of T now, by the way, kind of the big guy we want to understand. So if this lock gives a bijection of sets, then we say that the telescope conjecture holds for T. So this is kind of one formulation of the generalized telescope conjecture for kind of TT categories. You ask that this is a bijection of sets. So every smashing tensor ideal is generated by some kind of compact objects. And we know a lot of cases where this holds, but of course there are many cases where this doesn't hold. So this is a kind of a lossy process. So instead, the goal of this talk is to find some sort of topological space, some sort of spectrum object, which classifies these more wild objects. And we want to compare them, compare these two objects. So I want to take like a philosophical push out of this diagram, push out, and this is going to be where this smashing spectrum object is going to live. So that's the goal of today's talk, is to show how we get the existence of this smashing spectrum, what it looks like. We're going to compare it to the Balmer spectrum, and then finally we're going to look at some examples. So that's the goal. But first, to kind of understand the construction of this, we're going to have to take a pointless excursion through some pointless topology. So let's do a pointless excursion. So throughout this kind of section, so L is going to be a complete lattice. So it's a a poset where no puns here, Ian. No puns at all. So it's going to complete lattice with a meet and join operation. And what's the kind of the canonical example of such a lattice? So if X is a topological space, then the set of opens of X is a lattice. So the ordering is by usual inclusion. The union gives the join, and for the meet, you take the interior of the intersection. So this is a lattice. So this is kind of the starting point for pointless topology. It's a lattice, but it also has more structure. So this OX has more structure. It is something that we call a frame. So what does this mean? So a frame is a lattice where if I take the meet over an arbitrary join, this is the same as the join. So the lattice of open sets, topological space, has this frame property. And this sets up a functor, O, which runs from topological spaces to the category of frames, op. Doug, I was talking about infinite intersections. Obviously, finite intersections is fine.
Okay, infinite intersections. All right. Thanks. Thank you.
Yeah, so we have this category of frames, op. So because it'll be relevant later, let me tell you what a morphism is here. So the morphisms preserve are those kind of maps which preserve finite meets and arbitrary joins. So we'll come back to this later. But there's a nice category, and we have a function like this. And the question is can we go the other way? If we start with a frame, can we cook up a topological space? And what do you need for a topological space? Well, you need points, right? We need to get back to the pointed world. And kind of the insight here, well, it's not really an insight, right? If I take the opens of the 1 point space, you know, the point, this would be what we call 2, just the lattice 0 less than 1. Right, so a point in topology is just a map from the point in. So what's it going to be on the other side? Well, it's going to be a frame homomorphism. So a point in a lattice L is a frame morphism P from L to 2. So this lets us cook up points from a frame. So what's the topology then? So I need to give you the points in the topology. So the spectrum of a lattice L is the space which are very suggestively called spec of L. So as a set, this is just the points of the lattice. So frame morphisms from L to 2. With opens U of A. So I look at my points, so P in spec L, such that if I evaluate A, I get 1, and here A runs through the elements of my lattice. So this gives me a topological space. Okay, so what I've actually described for you is an adjoint pair from topological spaces to frames. Okay. So before I go on, I'll just say that this definition of a point might be a bit strange to some people. So here's maybe a more familiar one, especially if you're familiar with things like the Balmer spectrum. So there is a bijection between points of L and meet prime elements. Of L. So what do I mean by this? So those elements where if A meet B is less than to P, this implies A less than to P or B less than to P. So kind of the usual prime condition we used to. Okay, and we'll come back to that later when we do an example. It's easier to see what the points are like this. So the idea of people like Stone, so this is very kind of classical work now, is that this adjunction here is kind of the basis for an equivalence of categories. Of course, if I take any old topological space, I pass to its opens and I move back, I'm not going to get the same space back, and vice versa with the frames. So the kind of the key idea that people had on this pointless topology is that this O spec can be used to form an equivalence of categories if we restrict to the necessary things on either side. So here's a definition of a sober space, which probably isn't the one that you're used to. So X in top is sober if X is equivalent to the spec of the opens of X. So if I go this way around, the fixed points are the things, fixed points of this sober spaces, and going the other way around, so L in frames is spatial if L is the opens of spec of L. Okay, and so here's kind of the theorem, which usually goes by the name of stone duality. Is there's an equivalence of categories from sober spaces to spatial frames. So what's the upshot of this? Why am I telling you this? Well, if we're kind of naturally given a frame, which happens to be spatial, as is going to be our case, then without loss of any information whatsoever, we can pass the space spec L, right? And then the opens of that are going to be L again. So this allows us to cook up a topological space whose opens kind of classify the things that we want. So that's going to be how we're going to be using this. And it's good to note, so this restricts to a further equivalence of categories now between those topological spaces which are spectral and frames that we call coherent. I won't define what a coherent frame is. I'm not really going to add anything today, but just as a reminder to people what are spectral spaces. So these are spaces which are sober. Well, we knew this already because I said it's a restriction of the above equivalence. It is. We have a basis of quasi-compact opens. The space itself is quasi-compact, and finite intersection of quasi-compact opens is quasi-compact. So these are also, of course, the spaces which arise as a spec of a ring. And we also know that the Balmer spectrum is always spectral. We'll see that in a second. Okay. So we're about done with our excursion through the pointless world. But one thing that might be a little bit unsatisfactory at the moment is I've said that the frame is spatial. If when I pass the spec and look at the opens, I get an equivalence. This isn't a very nice checkable condition. And that's not what we use. So we'll just note there's a more intrinsic definition of what it means to be spatial. So L is spatial if whenever I have the relation that A is not less than or equal to B in the lattice, then there's a point P such that P of A is 1, the maximal element of my lattice, and P of B is 0, the minimal lattice element. And a lot of ways people like to phrase this is kind of L has enough points. It has enough points that it can kind of distinguish between all of these relations and separate all the points. So the point P witnesses the fact that A is not less than or equal to B. Okay, so this is kind of some very classical machinery of stone duality, and now what we're going to do is we're going to apply it to the TT world and see what we can't cook up. And the best starting place for this is going to be the Balmer spectrum, of course. So let me start by recalling, Balmer's definition of the Balmer spectrum. So just recall that T again is going to be a rigidly compactly generated TT category. And for this section, this means I get to avoid ever talking about radical ideals, which is nice. So here's the definition of Balmer. So the space SPUC T of the compacts, so as a set, these are the prime thick tensor ideals of T omega. By prime here, I just mean that if A tensor B is an element of P, then A is in P, or B is in P, just like with our ordinary commutative algebra. And I need to tell you what the topology is. Well, the topology is going to be defined through its closed sets. So with the basis of closed sets, given by these kind of supports. So these are those P and the spectrum. Such that X is not containing P. And here, this is as X runs through the compact objects. So the closed sets are generated by these supports of compact objects. And the example that we need today is the kind of easiest one somehow. So if R is a commutative ring, then there's this standard homeomorphism between just the usual Zariski spectrum of Zariski topology and Balmer spectrum of perfect complexes of R modules. So this is Balmer's kind of the way Balmer defines it in his paper. But there's a kind of a pointless way to do it as well. And this was recognized by, so this is kind of definition 1. And for definition 2, we're going to recall a theorem. This is a theorem of Koch and Pitch. They prove the following. So what we want to do is we consider the lattice. So I'll try and make it very obvious. I'm using a very curly T here. T of T omega of thick tensor ideals. Okay, so this thing is a lattice. And what do they show? Then this curly T omega is a coherent frame. Okay, so they show us a coherent frame under the assumptions I've given. If you're not rigidly compactly generated, you have to take instead the frame of radical things, but let's not worry about that today. So by what I've just said in a kind of pointless excursion, this implies the existence of a space. So there exists a space, a spectral space even, spec of T of T omega. Whose lattice of opens is this lattice that we began with. Okay. So they proved that there is this space. Great. So then we need to relate it to what we have, right? Let's hope this is the same as something we know. And indeed, I don't know why I switched to orange. Let's go back to normal color. So there's the bijection sets between this kind of intrinsically defined, through the lattice point of view, spec object and the Balmer spectrum. So they at least recognize the correct points. So the points here are exactly the prime thick tensor ideals. And this is followed by this definition of points I gave of being neat prime. But at this point, the topologies are actually different. And this might be time to panic if we couldn't now kind of use some nice spectral space theory. So recall, or guess, learn if you haven't looked at spectral spaces so much. So if X is a spectral space, as in both the Balmer spectrum is a spectral space, we know this, and this space here is a spectral space. There exists kind of a dual spectral space, or inverse spectral space, X, and I'll use a check. And this usually is called the Hoekstra dual. How is this defined? Well, it has the same points as X, so that doesn't change. And what's the topology? So the opens of X check are the so-called Thomason subsets of X. And what are these? These are things that form V, which I can write as a union of VI's, and VI is closed with quasi-compact complement. So this is how I cook up a new spectral space from any given spectral space. We have neat facts like the dual is just the thing we started with. So on the lattice point of view, the fact is that if I have any coherent lattice, I can actually flip the lattice upside down and take spec of that again. It's still a coherent lattice. The points end up being the same, and the topology ends up being described like this. So this also has kind of a lattice theoretic point of view. And essentially what Hock and Pitch proved, their main theorem, is the following, is that if I take the spec of T omega from the lattice, this is actually homeomorphic to the Hoekstra dual of the Balmer spectrum. So this is kind of the key point. This is kind of the key point. So completely using kind of this pointless topology, they managed to recook up Balmer's spectrum. And what's more, they retrieved the classification, Balmer's classification result. So what was Balmer's classification result, those of you who don't know? Well, Balmer said that if you take this spectrum, this Balmer spectrum, and you look at the Thomason subsets, this is exactly the thick tensor ideals. Well, this follows from this formalism quite easily. The opens of this space are just the thick tensor ideals, and by the definition of this dual construction here, we see that the opens correspond exactly to the Thomason subsets. So this is a kind of a lattice theoretic interpretation of Balmer's classification result. So this is kind of our first space. The Balmer spectrum has been computed in a lot of cases, and it's been used for a lot of things. And now what we're going to do is we're going to look at the smashing spectrum. So this will be our new toy, and we'll spend the rest of the talk discussing it. So we're going to denote by, I'll try to use a very exaggerated S of T, the collection of smashing tensor ideals in our big TT category T. So just to recall, this means that S, I have an I here, T is a localizing subcategory, and 2, we have a right adjoint R of I preserving coproducts. Another way to think about these things is they're also kind of kernels of smashing with idempotent objects. That's another way to think about them. So this is our kind of object of interest, this big collection of smashing tensor ideals. And the result that I want to talk about builds upon quite a lot of kind of previous work. And I think there's kind of three main steps that built into this. So I think the first kind of theorem I consider, an ingredient to this is a theorem of Henning who proved, I believe, in 2000, that under the assumptions of rigidly compactly generated, this ST is a set. So this is a really good start. I mean, as I said, if we just look at the collection of all localizing subcategories, we don't know if this is a set or not. But here we always know that we're a set. So we're off to an okay start. The next key result that goes into this is a theorem of Balmer, Krause, and Stevenson. A few years ago now, they proved that S of t is a frame. So at this point, you're super close, right? I mean, if you go through this kind of pointless point of view that we spoke about, we now have this frame. All we're missing is that this frame is spatial. And this is kind of the missing link that appears in mine and Greg's work. So myself and Greg Stevenson proved that S of t is a spatial frame under the rigidly compactly generated assumption. So quick note on the proof of this. I mean, it goes through some interesting kind of steps. I think it kind of uses these module categories that appear in the homological spectrum and things like this. It's not just kind of a straightforward check. We kind of move between idempotents in various places. But we do successfully show that this frame is spatial. And now we're on the money, right? Because I can give the main definition. We'll put it in red because it's so good. So there is a sober topological space which I'll denote book S of t, the smashing spectrum of t. So this is a space. I need to tell you how it's formed. So the points are the meet prime elements. As we discussed earlier, and the opens of this smashing spectrum are exactly this lattice S of t. So we've cooked up an invariant, a topological space whose lattice of opens is the lattice of smashing tensor ideals of the category. So this comes kind of instantly with the usuals that you'd hope for with such a thing in the TT world. So we have things like if X is now any object of T, we get a support, a smashing support corresponding to the object X, completely analogously to how Balmer defines it. These are just those prime elements where X is not in P. So this is kind of the native support theory. For those of you who know about the story, there's also kind of support in the style of Balmer-Favy. We define this. So kind of a more nuanced support, but this one is fine for now. And I just want to highlight a warning, which I guess isn't a surprise in hindsight at all, but the topology is not defined, is not generated by supports of compact objects. So I write this down because for the Balmer spectrum, we're able to write down the topology using to support compact objects. Here, that's not the case. We expect trouble, when the telescope conjecture fails, and this is exactly when this is going to fail. We'll see an example later. But the point is, like, you couldn't have kind of just written down this space and written down the correct topology, really. I mean, it wouldn't be very hard to just sit down and write down the right thing. We really had to come from this pointless point of view to get to this stage. Okay. Here's a question, which I would love to know the answer to. Is S of t a coherent frame? We don't know if the smashing spectrum is a spectral space in general. We know some kind of side bits about this. So we know that this space is quasi-compact with a basis of quasi-compact opens. So we're so close, right? We're sober, it's quasi-compact, basic quasi-compact opens, but we don't know, so what we're missing, finite intersections of quasi-compact opens. Quasi-compact. We're still missing this to show it's spectral. So. Okay, so now we've introduced our new gadget. We have this smashing spectrum. Well, it can be no good unless I can tell you exactly how it compares to the Balmer spectrum and what we can do with it. So let's compare some spectra. Okay, so what we need to know is the following. So there is a morphism, that's a frame morphism. So recall I told you what frame morphisms were earlier. They're those maps which preserve finite meets and arbitrary joins. So the following is a frame morphism. So we can go from the lattice of thick things to the lattice of smashing things, and it's exactly as I said in the introduction. I take kind of a thick tensor ideal here, which I've called P omega for now, and I just map that to, not that, the localizing subcategory generated by it. So this is a frame morphism. This emits a right adjoint, so there's a Galois connection. Right adjoint G what does this do? Well, it takes P and it just takes P intersect the compact objects. That's what it could be. So I just want to note that this thing is a map of locales. So we don't know. So here's a question mark. Not sure if frame map. So this is just a map of locales on frames. But the way that we've constructed these spectrum objects through the lattice point of view, everything's kind of nice and functorial. If I have a morphism of frames, I can just pass it through this stone duality and get a morphism of spaces going the other way. And that's what we do. So here's a theorem. I'll tell you some properties of this map. There is a continuous morphism let's call it psi from the smashing spectrum T into the Balmer spectrum of the compact objects. But here I have to take its Hoekstra dual. Right? If I'm cooking up from the lattices, when I get out to the Hoekstra dual, I don't know that this space is spectral, so I can't take its Hoekstra dual, it might not exist. So we're kind of reduced to this sort of map. But I mean, this data here is completely equivalent to the Balmer spectrum. And if you unwrap what stone duality actually does, it tells you that that phi of some p is just going to be p intersect the compact objects. So this is a continuous map. But we can say more. We can actually say some nice things about the map. So here are some properties. So property 1. This interacts nicely with kind of the native supports. So if X is a compact object, then the pre-image of its Balmer support is its smashing support. Good. Nothing too crazy going on. 2. This map psi is surjective. So 3, psi is a homeomorphism if and only if the telescope conjecture holds. Right, this just follows because if the telescope conjecture holds, then this lattice of thick tensor things is in bijection with the lattice of smashing tensor things, and this equivalence is passed through stone duality to a homeomorphism of spaces. But what's the last thing we can say? So 4, so psi is a quasi-compact map. So what does this mean? So if W in the dual of the Balmer spectrum is quasi-compact, then so is its pre-image. Right, so this is it's a mild, but it's still some sort of bounding property on how bad the smashing spectrum can be. You know, how bad can the lattice of smashing tensor ideals be? How badly can the telescope projector fail? I mean, yeah. I mean, even just the fact that this space is quasi-compact. So, because this thing is quasi-compact, it implies there's no T with, you can start bounding how bad this thing can look. You know, N is not quasi-compact, so there's no TT, compact generates TT category whose lattice of smashing things gives rise to this. Okay. And just a side note, why would I care if the space is spectral? So if this is a spectral space, we get a surjective map. Now I could take the dual of the smashing spectrum into the Balmer spectrum. This is surjective. And in Balmer's original paper on the Balmer spectrum, he proves that the support for the Balmer spectrum is kind of the universal such support. And then we can kind of rely on that to get some of our results as well. So it kind of lets us sidestep some things. So in the last 10 minutes, I just want to run through some examples of this thing in action. So example 1. Just following. It's just a sanity check that everything works as you'd hope. So if R is a commutative Noetherian ring, then by work of people like Newman, we know that dr satisfies the telescope conjecture. So, let's say nothing too interesting happens. This map phi from the smashing spectrum of dr is just homeomorphic to the dual, the Balmer spectrum, which again is just dual of this. So in the Noetherian case, nothing interesting is happening, but this should be exactly as we'd hope, right? The Noetherian case is very tame. We know things like there's a risky spectrum in a Theorem ring is always an Noetherian space. I mean, we shouldn't expect things to go wrong here. The telescope conjecture holds. Everyone's happy. So let's be a little bit less happy. Example 2. So it's clear that the interesting examples happen when the telescope conjecture fails. We know a few instances where it does fail. So obviously there's the example by Keller, which is essentially one we're going to do here, and also work of Bazzoni and let's make sure I get this right. Stovacek. Yeah, I think I did the accents okay then. So by work of Bazzoni and Stovacek, we also know for a lot of kind of rings of global dimension 1 what the smashing tensor ideals look like. So here's going to be our example. So AMK, I can't draw a frac M, unfortunately. There's going to be a non-Noetherian rank 1 valuation domain. And if you want an explicit example of this, I can take the following, so the following filtered colimit of FP of X along the Frobenius map. So I take this colimit over the Frobenius. This is called the perfection of FP. This is such a ring that will do the trick. So what does spec of A look like? So just the normal Zariski spectrum. I'm going to draw it as follows. So I have the ideal 0. That's the generic point. So I have a specialization down to the closed point.
Excuse me, in that colimit, are you sending X to its pth power?
Yeah, I think so, right? It's the Frobenius map.
Okay, all right.
Yeah, so I have this. So spectrum has 2 points. But we can now look at the frame S of D of A. This is fully known and it looks as follows. I have the whole thing sat at the top. I have the localizing subcategory generated by M. No, M is not compact. This is exotic. This is why telescope conjecture fails here. I have D M of A. So this is the localizing subcategory of those compact objects supported at the closed point M. I have the localizing subcategory of Q mod M. Q here is my function field. And here I have 0. So this is what the lattice looks like. Good. And now we look at the meet prime elements of this. So the meet prime elements have to not be the top element, so it can't be D of A. Let's take a look. This is meet prime. This is meet prime. This thing here is not meet prime. 0 is meet prime. So we get meet prime elements. Log M. this dm of A and the subcategory 0. Because this frame is finite, it's going to be coherent. So I'm going to kind of switch to the Hertzsche dual here so we can compare it directly to the Zariski spectrum. So the smashing spectrum of this derived category, and I've flipped my specializations, looks as follows. dm of A 0 like this. So I get a space with 2 generic points and 1 closed point. You can see that these two things are not the same as expected by the result. Good. And now I can also just remark the following. So if we were to topologize this spectrum object by supports of compact objects, we get opens the empty set, the whole thing, and the set P, block N 0. So we have these 3 opens, and the resulting space is not even sober. So somehow we can't just rely on looking at the compact objects to generate the topology, which is completely as expected when the telescope conjecture fails. So what are the types of things that we want to do eventually with this smashing spectrum? Well, we have a lot of kind of reconstruction results using the Balmer spectrum already. If the Balmer spectrum has certain properties, we can break the category apart over it and rebuild it. The smashing spectrum is either going to be equivalent if the telescope conjecture fails, holds. If it fails, we're going to get a finer splitting using this kind of finer space. That's kind of the plan we have for this. And I will stop there. Thank you.
Thanks, Scott, for that.
Oh, and before I finish,
sorry.
I just want to advertise this while I'm here. This is a conference proceedings which I edited with David Barnes, Magdalena Zurich, and Marcus Schimmick. It was based off John Greener's 60th birthday conference. I think a few of you were there. And I think some of the papers appearing in this LMS lecture note series are going to be of interest to a lot of people who attend this seminar. And it should be out at the end of the week. There we go. Now I'm done.
Okay. Yeah, thanks, Scott, for your talk. And can we all please unmute ourselves and give the speaker a round of applause, please? All right. If you have any questions for Scott, please either unmute yourself and speak or put them in the chat.
I have a question. That example, that last example of yours that involved the colimit under Frobenius, used a word that involved perfect. What was the word for, you had a term for that, what was it?
Oh, it's the perfection of this FPX.
Okay. And what if you, what if you started with, instead of FPX, you started with a truncated polynomial algebra. So you set x to the p equals 0, and then in the next one, x to the p squared equals 0, and so on. Is there a name for that ring? Is that an example you've thought about?
I have no idea, Doug, but there's probably people here who can tell you the answer to that. So
I mean, I'm asking that because if the telescope conjecture fails in chromatic height 2, there's going to be a ring in there that looks in it there's going to be a ring that looks like that. It's going to be your perfection of f p to the x, except it's truncated in the manner I described. So I'm wondering if people like you have thought about such rings.
I have not, but I would hope someone has.
Okay, thank you.
May I ask a question / suggestion?
Yeah, please.
Okay, so there's a paper by Niemann called oddball Bausfield classes. Perhaps you haven't looked at that example. It's a non-Noetherian ring whose nil radical is too big.
Right.
So I wonder what happens with your smashing spectrum of this ring.
So this is the oddball Bausfield class.
The oddball, yeah, that one.
Yeah, no. So I think yeah, it satisfies. Do you mean telescope there, Greg?
It satisfies the telescope conjecture.
Wait.
I don't know, I'm asking.
No, I think it's not. Yeah, no, I think it does satisfy. So the smashing spectrum looks just like the Balmer spectrum in this case. So, you know, still the smashing spectrum isn't fine enough to really capture all information, of course. I mean, there's still wild things out there. So in the preprint with Greg, we also introduced something called the big spectrum, which looks at even more, you know, horrible things. We look at basically prime localizing ideals. But the problem is, again, we don't even know if this thing is a set. Yeah.
Okay, thank you.
Yeah, thanks, Leo. Any more questions for Scott?
18 horas.
Oops, sorry.
Yeah, there were a few comments. Okay,
I
saw
think
this.
the comments in the chat have been taken care of.
Yeah. And the last one, the perfectoid ring one, I'm not so sure.
Yeah.
Oh no, yeah, that's fine. And I wanted to ask you, well, it's not a question, and I think the answer is very simple. When you quoted that result by Balmer, Krause, and Greg, even there, T needed to be rigidly compactly generated, yes? Yeah. I think you said rigidly compactly one after, and just there, I think you assumed that you're still assuming.
Yeah, no, I've assumed it throughout the entire talk.
Yeah. Oh yes, you said it at the very beginning, I think. Any more questions for Scott? Right. Okay. And Scott, before you go, would you like to say anything more about that book? Like you said, it's going to be out by the end of this week. Out how?
It's just a collection of papers based on, you know, interests of John Greenlee's mainly, but a lot of what appears in there is kind of, you know, Balmer-esque TT categories, like covariant homotopy theory, quite a few nice survey papers. I just thought it would be appropriate to the crowd.
Yes, of course. Okay. Thanks again. Okay, there is a comment in the. No. Yeah. Thanks again, Scott. And we don't have a seminar next week.
Could you show that slide again?
Oh, sorry.
Which slide?
Yeah. FPX?
No, the book, the one about the book.
Oh, the book, yeah. For you, Doug, we can sort that out. Let me reconnect my iPad. It's coming.
Yeah.
There we go. Yeah, and Ian's posted in the chat a link to the Cambridge
Right.
University Press. Yeah, according to them, the ebook should be out any day now, and the print version's in November. So,
Okay. Yeah, thanks. I'm looking forward to having a look at this book.
am I okay?
I was saying that the okay.
Am I okay to
No,
stop
go on.
sharing now, Doug? If you've got the information you need.
Yeah, thanks very much.
And I was mentioning the next talk, to the best of my knowledge, is on the 17th. But if there's something that needs to be scheduled before then, I will let people know when I know more. Okay, bye-bye.